Students, the topic which we'll discuss today is the first part to understand Archimedes' principle. Archimedes, the great scientist who was on this earth in an era which was before Christ, he is known to have established his own principle way back in 287 BC, that is before Christ. So as old as almost 2300 years back, or even more than that, somebody had really thought a lot about some very unique principle. And let us enjoy that concept, which is Archimedes' principle or concept of buoyancy or buoyant force, and try to understand this, because this is one principle which we will be using on and off every time, knowingly, unknowingly. Take an example, a simple example. As a young child, you must have filled some balloons with a lighter gas, and that balloon would go up into the sky. Some of you could be aware that it is filled with helium. Now, helium is lighter than air. That's what we often say. But we can also say that it gets a buoyant force so that it can float, being its density is less than air's density, it can float above a layer of air. Or one very interesting example I'll give. A story which all of you must have heard when you were young. A crow, which was feeling very thirsty, found an earthen pot somewhere. He was very happy, it was very happy. That crow went up to that earthen pot and sat on its edge to look for water. And yes, there was adequate water in that earthen pot. Crow was quite happy, but the problem came in. The water was a little deep than what crow could reach up to. Crow, has a beak, and that beak could not reach up to the level of water. Crow was smart. He had somehow learned Archimedes' principle long back. So what did that crow do? It went around, looked for small stones, kept adding the stones into water, and slowly that level of water kept on rising. He did it till he was comfortable, that crow was comfortable to get that water into its own beak and drink that. So he drank, went away, but unknowingly he had practiced Archimedes' principle. Now what is it? Okay, we'll come to Archimedes' principle later. First, I have to talk to you with some fundamental concepts which all of you could be knowing or should know both way. If you are knowing them, very well. The concepts which I wish to share with you are simple. The concept of mass, concept of weight, volume, concept of what is fluid, and concept of buoyant force or Archimedes' principle. So these are the few things which we must know. Before we, of course, one concept I forgot to write: density. And then, of course, relative density as well. We will understand these concepts first. Do some activities around them. We must understand the things thoroughly, so we are going step by step. Let us give some 3 to 5 minutes just to browse through these concepts. See, what is concept of mass? Mass is nothing but the material which object actually holds or that object possesses. The material inside that object, typically called as, say, atoms or molecules, they are held tightly in an object. the tightness or closeness of those atoms or molecules will decide that mass of that object. See, if something looks big, may not necessarily have more mass. For example, if you take a handful of cotton or a sponge or a foam piece, it may be big in size, but may not have that much of mass, because mass is nothing but a measure of its material. Then you know that if I take one small cubic centimeter of steel, same size of wood, same size of foam, or even same size of aluminium, these two are metals, but you will find that this is heavier than this, they both are heavier than wood, and they three are heavier than foam. So each has the same size but different mass. So mass is a content which is inside that object. That will not change whether you are on earth in Pune, or you go up to Delhi, or maybe travel up to Russia and go even upwards towards northern pole. Mass will not change. Or if you go to maybe moon or some other planet like say Mars, mass of that object will never change. Yes, but what will change is its weight. Because weight depends not just on mass, it depends on the gravity that pulls that object towards itself. So it is nothing but mass into acceleration due to gravity. That is your weight of the object. That will change from place to place. Even on the earth, it may not be same. If you are maybe on some seashore, it may have some different weight. If you go on top of Himalaya, it may have very different weight, because you have gone up, the gravitational pull is less out there. If you go right to the northern top of the earth, or pole of the earth, or southern pole of the earth, again it will have some different kind of weight. And what if you go to moon? Then something which is, now weight is measured in kilograms, we know. Sorry, mass is measured in kilograms, that we know. Being weight is mass into acceleration due to gravity. Normally we consider that to be 9.8 meter per second square is the acceleration due to gravity. M into G is weight of any object, and that is not exactly kilograms, that is measured in newtons. So 9.8, just to put it, we can say 10. So whatever is the weight or mass of the object, if it is 10 kg mass, then its weight will be approximately 100 newtons, or maybe 98 newtons to be more precise. So almost 10 times is its weight, because the measure is different, the unit is different. That is the concept of weight. You know, it depends on gravitational pull. If the gravitational pull on the moon is 1/6 of that of the earth, then what is weighing 100 newtons here will weigh approximately 17 newtons on moon, because moon has much less gravity if compared to the earth's gravitational pull. And what if you can go to a planet like Mars? Mars has approximately 0.4 or 0.38 gravitational pull if compared to Earth's gravitational pull. So naturally 100 Newton weight of some object on the Earth will show reading of approximately 38 Newtons when you are on Mars. So I guess it is clear, but will the mass of that object change? Mass does not change. Whether you are on Mars, on Earth or on Moon, mass does not change. Weight changes from place to place. These two concepts are clear, I guess, to you. Now volume, what is volume then? Volume is a three-dimensional shape which is occupying some mass inside it. So any three-dimensional object occupies a space, that is called its volume. A space occupied by three-dimensional shape is volume. Now if I take a coin and drop it into a bucket full of water, coin made up of say aluminum, the aluminum coin will also sink easily. Or say if I take zinc, it will sink easily. Even steel, will sink easily. But you know that you can make a sheet out of any metal because they are malleable. So you can start hitting that coin or that cube and make a long surface of it. Now it may perhaps float easily on water. It may not sink. So one small piece of steel or aluminium can easily sink, but you can make a huge sheet out of the same mass. This can float because that's the principle why ships can float over water. Because ships are made up of steel mainly, still they can float. Though steel we know is quite heavy than water because its volume is increased. They can easily float, such ships or such shapes. Should I put it this way then? What we are changing is not the mass, but we are changing its volume. So there is something called as mass and volume. If this ratio, mass by volume ratio, can be modified because you can increase volume of something or decrease volume of something, accordingly its density will change. So this is called as density of some object. Density is nothing but ratio of mass to volume. If I take once again 1 cubic centimeter, that means all sides are of 1 centimeter length. So this becomes a cube of 1 centimeter from all sides. If this cube of water is taken, so water of this size is taken, its mass is equal to 1 gram. 1 gram mass for 1 cubic centimeter. This is cubic centimeter, centimeter cube or cc. This is also called as cc. 1 cubic centimeter is equal to 1 gram. If I put it in this formula, it is 1 divided by 1. Mass by volume. So answer will be 1. Density does not have any kind of unit because it's a ratio of mass to volume. It does not need any unit. So density is 1. Density of water is considered as 1. This is of course at about 4 degrees Celsius. This is exact true at 4 degrees Celsius. At say 20 or 25 degree, which is a normal temperature around us, this is not exact 1, but it is 0.998. You can straightway say as 1. So water has a density of 1. Any object which has density more than 1 will sink. It is heavier than water, so it will sink. Any object which has density less than 1 will float. So mass of say 1 gram of steel, if converted to a large size and given a shape, something like this, so it has a volume. This volume could be say 5 cubic centimeters, 10 cubic centimeters. Then 1 gram divided by this 5 or 10 will decide its density. So it could be just 0.5 or 0.6, 0.2 density and it can float. That's the reason why ships float. The density is changed by increasing volume. Right? So that's the concept of density. And when density is spoken in terms of water, like water has density of 1, Some objects may have 2, 3 or 2.5, 7, 6 and likewise they are heavier than water. Some objects may have less than, like wood, foam may have density less than water. So when we talk in terms of density, in terms of or relative to water, it is called as a relative density or specific density as well. So each object has specific density relative to water. That's one more concept you must understand. So that's the density. So that is one more concept we have discussed. So I just rub off those concepts we have already discussed. Now we talk of fluids and solids or liquids. See, gases and liquids both are fluids. Fluid has two specific characteristics. It can be easily D-shaped. You can change its shape very easily. You know, water can be poured into a glass or a jar or a bucket or a tub. So it can change its shape according to the container. That means it can be D-shaped or deformed very easily. So is even true with gases, you know that. And they can flow from high to low. These gases or liquids can flow. So they together are called as fluids. Even fluid, plasma is also a fluid, but we will not talk of plasma. Right now only liquids and gases, they are fluids. Now when we take a large container having some kind of fluid and dip some object into it. You are holding an object and dipping that into it. It is heavier, fine. So you know that as this level from top decides the pressure of fluid, because more deep you go, more will be the pressure from top. That's a simple law of pressure in liquid, and at this level the pressure will be same from all sides. At this level, wherever this is the top surface of the object. Now what happens to the lower surface? That is deeper. So naturally being it is deeper, it will experience more pressure, but now it cannot experience it from the top because this is experienced from the top surface of it. This experiences a force which is pushing it upwards. This is nothing but your buoyant force or buoyancy. Any object which is sunk or immersed in liquid, partially or wholly or fully, experiences at its lower surface a force which is pushing it upwards. That means it is opposite to the weight of it. That force is called as buoyancy or buoyant force. It will be decided by density of the liquid, by the volume of this liquid, the volume of this solid which is sunk into that, and so on. Now, Archimedes found out one very interesting thing. I'll talk of this principle at more depth or in more detailed way after this session is over. But in this session, let us first know, Archimedes found out one very interesting thing. We all may experience that when some object is heavy in the air, when you dip it inside water, you feel it lighter. You feel as if its apparent weight has been reduced. Actual weight is same, but being it is in water, it experiences that buoyant force. So we feel it lighter. And when you dip it inside, like the crow experience, that level of water rises. Earlier it was this. Now some level of water rises because this is sunk into that. Or you can say, this object displaces some water. If you imagine that this container is absolutely full and you dip that object, water will spill out. And if you collect this water which has come out from that container, you will realize that the reduction of weight of this object when it is immersed in liquid, reduction of weight, only reduction of weight, I am repeating it, is equal to the weight of displaced liquid. That's the Archimedes principle. Once again, just to repeat in the summarized form, when you submerge some object, it displaces liquid. This becomes little lighter the reduction in its weight, in its apparent weight of course, that reduction of weight is equal to the water or liquid that is displaced by this object where it is sunk. That's the Archimedes principle. Here we go for activities and enjoy this principle to its part first. Students, we are beginning with activities which will take us to Archimedes principle. But before we directly jump onto Archimedes principle, we need to do some simple activities to understand some fundamental concepts. We'll be needing this instrument. This is called as measuring cylinder. Usually capacity of this cylinder varies from instrument to instrument. This is up to 25 ml. Being we are measuring water in this, 25 ml is equal to 25 cubic centimeter or cc. Both are same. 1 cc is equal to 1 ml of water. You can take a note. This gives 10, then 20 and 25. So between say 10 and 20, this is 10 ml, but there are 20 markings in between this. That means one line is of 0.5 ml. One line is of 0.5 ml, right? So that's the least count of this instrument. So between 10 and 20 ml, that is in 10 ml total of its height, there are 20 lines. So one line represents 0.5 ml. This is the least count. We will be using a spring balance that has a capacity to measure up to 100 grams. But we are measuring weight, so we must talk in terms of newtons. That is 1 Newton. Because you know that 1 kg is 10 Newton. This 0.1 kg equal to 1 Newton. So capacity of this spring balance is 1 Newton or 100 grams. Right? Now between 0 and 10, so the marking is from 0 to 10 grams, there are 5 lines. That means each line represents 2 grams. So the least count of this spring balance is 2 grams. So some fundamental things we must know. We will go for activity number 1. Very interesting activity. We will try to find out volume of this ball. Ball is a perfect spherical object, but we'll find out its volume by water displacement method. Now what should we do for this? The first thing, we will just insert this hook into this ball and roll it so that it can be screwed inside. So I have put this inside. Okay, this is done. Let us try thread to this hook. So this object is now ready. You can immerse this in water. Okay. So negligible volume would be added by this hook, but it is so negligible that we can just ignore it. Now next step. This is called as overflow vessel. It has this spout through which water will come out. I'll collect that in this beaker. Let us first fill this and let some water come out of it. Okay. So now the level of water is exactly at the lower marking of the spout. I'll just empty this beaker and place it once again. Now if I dip this into this overflow vessel, you know that it will displace water, and displaced water will come out of this spout and get collected into the beaker. Let us try out gently. Let it go down gently, and water will come into the beaker. Now, as much was possible, water has come out. It will not come out any further. So I can just remove this and keep it away. The displaced volume of water is equal to volume of this ball, right? So let us measure it. I'll transfer this to empty measuring cylinder and look for its reading. So let us look at it. It is 12.5. This is showing 12.5 ml or cubic centimeter as the reading. The reading is 12.5 ml. How will you record this reading? Always keep it on a plain platform and look at it from same level. Your eye level should be here only. You should not look from this side or from bottom side. You should look from horizontal plane and then record this reading. So I am holding it up. So it is 12.5. Okay. Students, we have seen volume of this regular object by submersing it into water and measuring its volume here. That water volume showed 12.5 milliliters or cubic centimeters. That means volume of this is about 12.5 cc, cubic centimeters. Of course, being this a regular shape, we can also find out its volume using mathematical formula. We'll do it later. But what if we have some irregular shape like a stone that cannot have any mathematical formula, but you can find out its volume by just immersing it in water, collecting water here and measuring it, right? I don't have any stone around me, so what will I do? I'll take a long bolt, insert several nuts into this. To make it heavy, we are putting in a lot of nuts inside, and then we'll use this as an irregular shape, because then this becomes some random shape. It does not have any specific formula then. So this is what we are using as an irregular shape. Let's know this. You can very well go out, find out a stone and do this activity again. I can place as many nuts as I can. I'll place so. Okay, I can fit in all the nuts given. Then I must tie a thread to this. Let us use some thread, maybe same thread which we have used for, I'll just make a small piece of it and tie it here. So we have tied knot of this thread to this assembly of bolt and several nuts. Now we will go with the same process. Take some water into this overflow vessel. Let the excess water come out. Once the flow stops, we'll empty this beaker and we'll place this again under this spout. Then very carefully you have to immerse this nut and bolt assembly into the overflow vessel and collect this water coming out into a beaker or any container. Let's take a look. Okay, some water has come out. We will transfer this water into a measuring cylinder and find out its volume. Okay, I am now reading the marking of this water level, which is 1, 2, it is 3.5. 3.5 ml is the volume of this total assembly. We can use one more simple technique for this. I'll just share that technique with you. This is understood by now, it is 3.5 is the volume. I'll just add some water into measuring cylinder, say up to marking of say 20 ml, right up to here. When we consider displacement of water, it may not have to come out always from the spout. We can simply see the level of water which will rise when I dip some object into this. Right now it is at 20. If I dip this nut and bolt assembly into this, let us see how much does it rise. I must immerse this completely into water. So this immersed completely, and let me also take a look at the reading. This has gone up to 23. No, 23 and 5.5, 23.5. Take a look. So earlier it was 20. Now after immersing this nut and bolt assembly, it has come up to 23.5. So the difference is 3.5 ml or cc. Same reading in both the cases. Right? So we have found out volume of irregular shape using water displacement method. We have talked about density of water. We also know it is 1. That means 1 ml or 1 cubic centimeter of water should weigh exactly 1 gram. Now we will do that experimentally as well. I am using one plastic bag and we will take 50 ml of water into this bag. 50 ml of water into this bag. I have already taken 25 in this. I'll transfer this 25 ml or 25 cc into this plastic bag. Take one more round of it. One more 25 ml water into this. Okay. So 25 ml is taken. I am just keeping it a little away. Let us take one more round of 25 ml. Okay, I have taken another 25 ml, adding that 25 ml into the same plastic bag, so it will be 50 ml. So 25 plus 25, 50 ml of water. Let us take spring balance now. See if its marker is exactly at 0, and we'll attach this hook of spring balance to plastic bag. Do it carefully without pulling this. Okay. I just now lift this plastic bag slowly and look at the reading. You will find the reading is coming out to 50 grams. So what does that imply? The mass is 50, volume is also 50. So 50 grams divided by 50 ml, the division will give you answer as 1. That's the density of water. We always talk about density of oil. We always say it is less than water. What is it? What is its effect then? Let us do one small activity to understand it. I am taking oil from this pouch into a vial. So already I have cut this, taken oil into this vial, and will add some water into this. Let us see. Oil is now at lower level. I am adding water from top. Wait for some time and you will find that water automatically settles down and oil comes up. Oil always comes on top of water because oil has less density than water, or it is lighter than water. So it will come on top. So here you once again understand the density of oil is less than that of water. Now one activity that you should do at home carefully. What is it? We know that we had taken some 50 ml of water into this. Similarly, take 50 ml of cooking oil in this bag. Take 50 ml of cooking oil. How will you take? You have measuring cylinder, measure oil into that, transfer it into this pouch. Make sure that this pouch is clean, because same cooking oil you will have to use, because you cannot throw 50 ml oil unnecessarily. So you may have to use it again for cooking purpose. Do it carefully. Take 50 ml into this. Weigh 50 ml oil using spring balance. See if the weight is 50 grams, less than 50 grams or more than 50 grams. And please convey your reading on the group. I will not tell you right now what should be its weight, but try that out definitely. So you understand how is the effect of density on its mass. Correct? This is one activity for you. You can see level of oil that is above water now. So oil is floating on top of water. We know that water has density of 1. Some of you could be aware that milk may have a density more than 1, or oil has density less than 1. But how do we measure it? There is a simple instrument used for such purpose or this reason. That instrument is called as hydrometer, or if it is specifically for milk, then it is called as lactometer. Basically what is done in that, some object which has a heavy part at the bottom is dropped in water, which will stand upright like this, and it will dip to some level in water. So if you mark this level for pure water, And similarly, if you take absolutely clear buffalo milk or cow milk and make the markings, remember that if in water it is dipped up to this level, then in milk it will be somewhere here. Milk has more density, so naturally it will float more. So marking for water, marking for milk is done, and in between you can have small markings. So if you get a milk in the morning from some supplier or some source, you can drop this lactometer into that and check for its purity. If the milk is mixed with water, the reading may come in between the two, right? So I'll begin with these steel balls. I'm putting these steel balls one by one into this dropper to make it heavy. I have filled several balls or steel balls into this dropper. Let us try to drop it in water. I'll just show you that it stands upright and it floats in water at it is submerged up to certain level. You just can find it out. Yeah. So you can see the level, mark it using a permanent marker. This level in water. You can also do one more experiment. This is a table salt. You can add salt in water. You know, salt water has more density than ordinary water. Try to drop this dropper, same setup, into water which has a lot of salt dissolved in it, and make the marking. So you'll notice there is a small difference between the two. This will float more in salt water because it has more density, right? If you put this in oil, it will sink more because oil has less density than water. And of course, I have already shared with you about milk. So make the marking for water, make the marking for milk, and use this as a lactometer for day-to-day checking of the milk quality.